All right, AP, let's take a look at Chapter 12, Chemical Kinetics, the rates and mechanisms of chemical reactions. Now, when we talk about chemical kinetics, there are going to be a lot of different types of kinetics that we go over, different types of studies that all refer to speeds or rates of reactions under various conditions. That's what chemical kinetics is. It's the study of the speed or rate of a particular reaction. Now, there are different ways that we can study rates. We have different types of rates. We'll be going over differential rate law. We'll be going over the integrated rate law. We'll be going over instantaneous. Messed up there. Instantaneous rate law. We'll be going over relative rate law, and then we'll, as a little extra, we'll be going over activation energy. Right. Remember, we went over this when we were talking about thermodynamics. If I was going to draw an exothermic reaction, right, I would have the energy on the y-axis. The reaction progress on the x-axis. Remember, the energy level of my products is going to be lower than the energy level of my reactants, right? So there's going to be a decrease in the overall energy in this system. That's going to be an exothermic reaction. But what I want to remind you of is this little bump in the graph. In order to make this, whatever this reaction is, happen, we have to elevate the energy situation of anything that's involved, the reactants involved, up to this certain point, and then once we reach this minimum amount of energy, the reaction can occur, and then we see this dip in the energy present in the system. This bump right here is the activation energy. Okay, the peak of that bump is activation energy. Now, because we are studying reaction rates and mechanisms of those reactions, it's going to be really important that we keep activation energy in mind, because without adding that energy, the reaction won't happen. Spontaneity is also important, but what I want to remind you of is a spontaneous reaction does not imply a rapid reaction. Okay, it does not. We've already gone over spontaneity or thermodynamic favorability. That means it's going to go on its own. It doesn't mean it's going to go fast. Remember, when we were talking about thermodynamics and thermochemistry, we never talked about the rate at which that reaction occurs. For example, diamond, like in a diamond ring, diamond turning into graphite is spontaneous. It is spontaneous, but it is very slow. It's so slow that it's essentially non-detectable even in an entire lifetime. A lot of times you'll see wedding rings passed down as family heirlooms, and they're still diamond. That diamond truly is turning into graphite, but so slowly, even over multiple lifetimes, it's non-detectable. It still looks like a diamond. A mechanism is a sequence of events, right? We have to, what is the mechanism part? A mechanism is a sequence of events at the molecular level, okay, down here at the individual molecular level, that controls the speed and the outcome of the reaction. Okay. Now we're going to get into factors that affect reaction rates, okay, that can affect the speed at which these things happen. And before we get into factors that affect rates, let's remind ourselves that you probably already have some exposure to rates in the past. If you've already taken physics before you've been in this class, you've seen rate probably as some sort of distance over time. Okay, distance over time. That's fine. That's rate. But in chemistry, we're not going to be talking about a distance. We're still gonna control the amount of time, right? It's always per unit time, whatever unit time is more useful for us. But in chemistry, specifically in this chapter, we're going to be talking about concentrations of reactants or products. So I'm going to have the concentration, hence the brackets, and whatever the change in the concentration of that particular species is over time is going to be my rate. In the simplest form, that's what rate is going to be. also these brackets, they represent concentration. The units for concentration is molarity, which is the same thing as moles per liter. Okay, so let's remind ourselves of those units. That'll come in handy in the future when you start to try to figure out what K is. But let's get into the factors that affect reaction rates. Now, a lot of this is common sense if you think about it. So the following conditions affect the speed of a chemical process. 1, the nature of the reactants. Some reactant molecules react in a hurry, others react very slowly. That has to do with the nature of those reactants. For example, when we look at the physical state, like the phase, right? We have gasoline liquid versus gasoline in the gaseous state. Liquid gasoline is not nearly as reactive as gasoline vapor. Okay, when you're gassing up your car somewhere, that smell that you smell, that's gasoline, that is actually more dangerous. It's more explosive than the liquid gas that you're actually putting in your tank. If you've ever wondered why all those signs are around that say that you're not supposed to smoke or have any sort of open flame around a gas pump, like obviously it's going to explode. That's why you don't want to do that. But it's actually not the liquid gas on the ground. It's not the liquid gas on the ground. Remember one time when I was young, someone spilled a bunch of gas on the ground in front of a pump, and I was really worried that the entire gas station was going to blow up. That liquid gas isn't actually the problem. It's the small amounts of vapor that are going to come off of that liquid gas. That's the problem, because it's a higher energy state. And so in order to react, or in that case combust, those reactants are going to be further up this energy scale and be closer to the activation energy. They're going to have a better chance of exploding. It's actually not the liquid, it's the gas. One of the things that we want to pay attention to is that in the liquid state, that gas is more dense, and in the vapor state, that gas is less dense. We want to keep that in mind as we go forward. We can have solids. Most of the time, when you mix a solid with a solid, you're not going to have a reaction. Most of the time, this doesn't always happen. There are reactions that you can just mix two solids together and they will react. Because remember, in order for two reactants to react, they have to come into contact with one another. And so when we have two solids, let's just assume we have two cubes, only the surface area of those solids is ever going to come into contact. Okay? Only surface area is in contact. So that means only the surface of this reactant and only the surface of this reactant are actually coming into contact. They have the potential to react. Nothing in the middle or on the opposite side of these solids is coming into contact. And in order to react, these species need to come into contact. Let's apply that to this more dense, less dense. When things are more dense, okay, they're not actually moving around with nearly as much energy. Okay, remember in the liquid state, the individual molecules are simply sliding around one another, but in the gas state, they are moving around very, very rapidly. In order to have any particular reaction occur, okay, it requires energy. Okay, we're going to need this energy to do what? To break bonds. And only then will the reaction occur once those initial bonds are broken. And then after that, then energy will be released when new bonds form. So once we get to this point, and again, looking at this graph, once we get to this point, the reaction it can continue just like we want it to. But to get to this point, we have to supply a certain amount of energy, the activation energy. And if we are further apart and we have the individual molecules moving at a faster rate, the individual molecules are moving faster. When they do collide, there is a better chance of there being sufficient energy to break the bonds within those at least two reactants. Now, once there's enough energy to break those bonds will be broken. And then the more favorable bonds, okay, once everyone is single within the reactants, the more favorable bonding pairs will form. And once that happens, we'll have a release of energy as the resulting products will be at a lower energy configuration. But we have to add this energy first, and it's going to be easier to do that when we have faster moving individual molecules. Whereas in a solid state, these things are moving as pretty much as slow as they can, because they're not allowed to even move around themselves like they are in a liquid. One of the best ways to get something in the solid state to react, right? You might think, oh, these are both solid because only the surface area is in contact. We're never going to get this to react. That's not true. We can simply put them in water. Okay, if we enter them into the aqueous state, this reaction can occur and it will occur. So we need to take into consideration the physical state of the reactants. Also, the identity of that chemical. For example, what is reacting? Usually ions of opposite charge react very rapidly, okay, because they are using what's called spelling the wrong word. Coulombic, okay, attractions. Coulombic attractions, pluses and minuses. When you have an ion of opposite charge, they're going to bring themselves together, and usually pretty strongly, especially if we have ions. That's an entire charge. It's a pretty strong attraction. Those Coulombic attractions will make that reaction occur a lot faster because there's an extra source of energy to move those things into contact with one another. Usually, the more bonds between reacting atoms in the molecule, the slower the reaction rate. Okay, so if we have, a simple carbon-hydrogen, there's only one bond to break versus maybe 4 bonds to break, like in this methane that I'm drawing right here. This is going to react a lot faster because there's only one bond to break compared to this methane right here where there are 4 bonds to break before that can occur. Remember, we have to put energy in to break the bonds, right, to satisfy this energy hump. Okay, and if there are more bonds to break, that's going to take more energy. It'll take more time because those collisions will be a little bit more rare. Substances with strong bonds, meaning large bond energies. Remember from Chem, bond energy is one of the things that we use to measure the strength of a covalent bond. Substances with strong bond energies, large bond energies will react more slowly. Why? Same idea over here. We have to break all these bonds, and breaking each bond requires more energy. If a certain bond has a large bond energy, that's going to require more energy. And so the collisions that result in that much energy are a little bit more rare. Okay, it happens. A few more things have to align just right, and so it's a little bit more rare for that to happen. So that reaction is going to take a lot more time. It's going to react more slowly. For example, metallic sodium reacts much faster with water than metallic calcium. And before we talk about why, I want to remind you, by looking at the periodic table, you can see that this is a 1A metal and this is a 2A metal. Right? Main group 1, main group 2. So metallic sodium reacts much faster with water than metallic calcium. Also, the oxidation of methane can be increased with an increase in temperature. Right? So if that's the idea, heat them up, speed them up. Right? If you are trying to break all these bonds in this methane up here, if you simply increase the temperature, because of the kinetic molecular theory, I hope you remember when we look at temperature, that is proportional to the kinetic energy present in that substance. And if we all have similar masses, all that's going to increase with temperature is going to be the velocity. Okay, the velocity is going to increase. And so if we have increased velocity, these things are moving faster. So when they collide, there's more energy present in that collision. It's an easier time to break the bonds. That means that reaction is going to progress a lot more quickly. Photosynthesis is very slow and changes very little with the increase in temperature. Right, so we have let's see. So we have what group on the periodic table is that substance? Okay, is that substance? This is going to react a lot faster because it only has to ditch one valence electron to reach that noble gas electron configuration. Calcium has to ditch 2 electrons to get to that noble gas electron configuration. So this reaction is going to happen a lot more quickly compared to metallic calcium. Changing the temperature. Remember, we're satisfying the kinetic molecular theory, KMT. Heat them up, speed them up. Okay, when they're going faster, they're going to hit harder, easier time to break those bonds. But again, these types of things are common sense, or at least stuff that hopefully you remember from Gen Chem. So we talked about the nature of the reactants. Next thing we're going to talk about is the concentration of the reactants. This makes sense, right? So if we have concentration A and concentration B, we're going to get a certain reaction rate because there's a certain amount of molecules present in this situation, and those molecules can collide. Now, if I add more A and more B, there are going to be more molecules and more collisions. At the same temperature, meaning the same amount of kinetic energy, therefore the same velocities, right? So that's not changing. If I have more molecules moving at the same speed, I'm going to have more collisions. And if I have more collisions, there's more of a chance that I'm going to have a collision that yields the appropriate amount of energy to break those bonds. So more molecules means more collisions. We can also change temperature. We can also change temperature. Again, heat them up, speed them up, like we mentioned earlier. The faster they move, the more likely they are to collide. Because remember, these things are very, very small, especially when you're looking at something in the gas phase or something in an aqueous solution. These things are very, very small, and because they're so small, it's hard for them to hit each other. And so the faster they move, the more likely they are to collide. So an increase in temperature produces more quote-unquote successful collisions that are able to overcome that needed activation energy, therefore an increase in reaction rate with increasing temperature. Now, this word successful collisions, this is the type of phrase that you want to include in your free responses. There are two major factors. Yeah, there are more, but there are two major factors that will affect whether or not a collision is successful. So let's get over here. So we need to collide with proper geometry, okay, which means orientation. They have to be facing the right direction when they collide, so proper geometry. Also, they need sufficient energy, meaning they need a certain amount of oomph when they collide. If they don't have the proper amount of energy, that is not, even if they collide, there won't be enough energy in that small system to break those bonds, allowing their reaction to progress. Here's a fun fact that you definitely want to memorize. This is a multiple choice question if I've ever seen one. So increasing temperature will increase the reaction rate. In fact, a general rule of thumb is that for every 10 degrees Celsius increase in temperature, there will be a doubling of the reaction rate. Okay, a doubling of the reaction rate. So that's a fun fact. Yep. All right, so next thing that will affect reaction rate is a catalyst. Okay, you've probably already been exposed to catalysts when you studied biology, because you all had to have taken biology before you made it into this class. You probably remember that a biological catalyst is a protein. They're called enzymes. They help to make a reaction go faster. And functionally, what they do is they take a particular reaction. Yeah, they would have this normal energy graph like this, like I drew up on the top of the page. And instead of having this very, very high activation energy point up here for this reaction to progress, it makes that activation energy only right there. And it makes it much easier for that reaction to take place because the activation energy has been lowered. One thing that you need to remember about a catalyst is that it most certainly accelerates chemical reactions, but the catalyst itself is not transformed. When I was in school, I remember catalysts as things that accelerate chemical reactions, but are not, but don't participate in the reaction. And what I was thinking of is you remember your, the different formula equations, like your complete ionic equation, your net ionic equation. You'd cross out those spectator species, those things that don't actually participate in the reaction. That's what I was thinking of. That they stay there. They don't actually react with anything. But to say that they don't participate in the reaction is completely wrong. They definitely participate in the reaction. They're the thing that makes the reaction go faster. However, they are not. Where'd it go? They are not transformed. Okay, you have a certain enzyme at the beginning. You have that exact same enzyme at the end. They participate. What they do, if you guys remember, they're larger molecules, and when they come into contact with two different species, two different reactants, what they do is they force those two reactants to have proper geometry. Right? They have forced them to have proper geometry because those two reactants can only hook up with those. The enzyme can only hook up with those reactants in a certain way, okay, and those active sites, and because of that because of the enzyme and the different Coulombic contractions within that amino acid sequence, it makes this sufficient energy thing almost non-existent. They just the enzyme kind of forces them together to react and break those bonds. Let's see. So, but when we are looking at a catalyst is a substance that changes the, again, rate of reaction. The reaction itself stays the same, right? Because that catalyst is not transformed in any way. It's kind of like a spectator in the sense that it doesn't change, but it definitely participates. It changes the rate of reaction by altering the reaction pathway. Most catalysts work by lowering the activation energy needed for the reaction to proceed. Therefore, more collisions are successful, and the reaction rate is increased. Again, just like when we're talking about temperature, heat them up, speed them up. When you get more collisions, more reactions. Or anytime that we increase the concentration of the reactants, more molecules, more collisions, more chances of a successful collision. Remember, the catalyst is not part of the chemical reaction itself, and it's not used up. Okay, it is not used up because you're not actually transforming the catalyst. It stays there. But even though it's not used up, it can become saturated. It can become saturated, which means you have more potential reactants than you have enzymes to facilitate their reaction, right? So the catalyst is doing its job, but you have a big line of reactants waiting to use that catalyst, and so simply by adding more reactants, you're not going to increase the rate at all at this point because that catalyst has been saturated. Okay, there's no more catalysts. I mean, they're working. The catalysts are working, but there's no spare catalysts that can continue to increase the rate. Here's one. Let's see. So peroxide H2O2 decomposes relatively slowly, into water and oxygen. That's why if you have hydrogen peroxide at home, it will go old, right? And if it's been there for a super long time, it'll probably have decomposed into two things that you're not really going to use hydrogen peroxide for, water and O2. However, any exposure to light accelerates this process. Okay, it makes it happen. Right? This exposure to light accelerating the process is why you always buy hydrogen peroxide in a brown bottle that's not clear at all. And you definitely want to keep it under your sink where there's no light. That's going to keep that hydrogen peroxide a little bit more intact for longer. And if you add manganese dioxide, the reaction will go extremely fast. You might have seen something like this on YouTube if you've ever seen something called elephant toothpaste. That is hydrogen peroxide and manganese dioxide. It just makes that decomposition into this and this extremely fast. You actually see it happening in front of you. One more thing I want to point out. The catalyst lowers the activation energy barrier, right? It makes this hump a lot lower. However, that's true of both the forward and reverse reactions. Forward and reverse reactions, they're both accelerated to the same degree, right? So I have a reaction that wants to go this way. It doesn't have to go up as far. But there is a reverse reaction that would come up this way. Here are the reactants. If energy is added to the system, they can have an endothermic reaction go back the other way. To the same degree, this activation energy hump is still lower, right? So it's easier to go backwards as well. Easier to go forward, it's easier to go backwards in the exact same degree. Some homogeneous catalysts actually appear in the rate law because their concentration affects their reaction. Like in this example of, let's see, that happens a little bit too fast. Let's not use that one. Well, when we're talking about having your catalyst become saturated, we actually include the concentration of the catalyst in the reaction. It's just over the arrow. Okay, it's probably going to be over the arrow. So you got like A plus B, and here's your reaction arrow. We'll actually include, not even on the camera, sorry. Sometimes they will appear in the rate law because their concentration affects the reaction. So we have A plus B reacting to form D. This concentration of this catalyst, which I represented here with C because I'm smart, this concentration is going to be important because this concentration is going to be one of the determining factors of the rate. If the concentration is very high, it's less likely that the catalyst will become saturated, and the rate of that reaction will increase massively. If there's a very small concentration of that catalyst, it's going to be easier for that catalyst to become saturated, and you're not going to be able to achieve quite as large of an increase in reaction rate. Next page. Last thing, for factors that affect reaction rate, surface area. Okay, surface area, like we were talking about with those solid reactants. When you only have exposed surfaces that are affecting speed, you're going to be limited to how much are actually touching. If you have a large surface area, you're probably going to see an increase in reaction rate. Except for substances in the gaseous state or in aqueous solution, reactions occur at the boundary or the interface between the two phases. And so when we have a cube and we put them together, okay, only molecules at this boundary are actually going to react, because those are the only reactants that are in contact with one another. And so if we increase the amount of surface area, right, more surface area coming in contact with one another, we're going to be able to increase the rate of reaction. The greater the surface area exposed, the greater chance of collisions between particles, hence the reaction should proceed at a much faster rate. An example, coal dust is very explosive, as opposed to a piece of charcoal. Um, this is one of the reasons that you see kind of random explosions in coal mines, why coal mining is so dangerous. Remember, coal is just carbon. Yeah, it's just carbon. And you can essentially burn charcoal at a pretty steady rate, like in a barbecue, at a pretty steady rate. It's not explosive. Like it's flammable, but it's not explosive. Coal dust is explosive because the individual particles are much more dispersed, right? It's not one clump. One chunk of charcoal that you would throw in your barbecue has a certain amount of surface area. Realize if you were to break that piece in half, you will have increased the surface area, more reaction. Break it in half again, more surface area, more reaction. So imagine that all the way down to the molecular level, where let's just say theoretically, it's super fine coal dust. You have as much surface area as possible because you have smaller pieces. And so because there's so much more surface area, the reaction rate is going to be increased significantly. And when you have the combustion, right, the combustion of charcoal, if you simply increase the speed, you have all of that combustion happen at once. That's an explosion, right? Very explosive. And here's an extra fact that the AP examiners love to throw in there. They love to throw in there. So this is a AP exam fave. Adding an inert gas has no effect on the reaction rate or the equilibrium of the reaction. Because if let's see, we have A plus B reacting to form D. If we simply add in an inert gas, okay, it's not going to participate in this reaction. It's not going to be a part of it. So even if we add some of this inert gas to this side, it's just going to be on the product side as well. It's not going to participate in the reaction at all. It's definitely not going to be consumed, kind of like a catalyst is, but this inert gas isn't going to do anything at all. So it's not going to affect the reaction rate at all, hence the word inert. All right, guys. I'm going to wrap up this video right here. Go ahead and move on to the next part.